Okay, I think we can get started. Well, thanks everyone for coming to the Digital Forestry, Digital Ag seminar series. Today we have Dr. Aardt to give us a presentation, but I'll let Dr. Crawford to the introduction.
Sure. So, thank you. I am really delighted to be able to introduce Jan. I have known Jan for many years. In fact, one of the things I thought about this morning was, when did I meet Jan? He did his undergraduate degree work at Stellenbosch in South Africa. And so I know it was after that. He went to Virginia Tech and got his master's and PhD in forestry, and then went to Belgium. And that might have been when I first met you. Yes. And for those of you that have been around a while, he worked with Paul Koppen at KU Leuven. And there was a relationship between KU Leuven and Purdue, and that was through Chris Johansson. So many of you know Chris. And then after that, Jan went to South Africa, and I think I saw you in Pretoria when I was down there. And then I was delighted later when he moved to RIT. He was recruited to RIT and has been there ever since. So he crosses the bridge in many ways from forestry to science. Science in terms of simulation, but science also in terms of technology. Both LiDAR and hyperspectral data have been, part of what he has used. And then more recently in applications, and that's been both in precision ag and in forestry. So we're looking forward to hearing more from you today.
Thanks, Elva. Well, thank you very much for having me. It's one of those things where you get so comfortable in your own environment. You think you're doing such fancy stuff with fancy people, and then you come to a place like Purdue and you're humbled again. It was just walking across campus this morning was really cool. I'm used to Virginia Tech and seeing these kinds of open campus environments, so it's really fun to be in a place like this again. And then someone just fed me a beef burger, so I actually need a nap, but we're going to try our best, okay? So I'm going to talk to you a little bit about the simulations we're doing, especially as it relates to forestry and agriculture. I've been really privileged to work with a bunch of people at RIT that can do these things very well. I'm not a trained physicist, I'm not a trained computer scientist, but I work with electrical engineers, mechanical engineers, computer engineers, physicists, and computer scientists a lot in the job that I work at it now. And I sort of want to acknowledge all the contributors. These are some of my students, collaborators. They're much smarter than I am, and I can say to this crowd, you can bleep that out of the YouTube video. But and this is sort of how the talk is going to go. I'm going to sort of focus on two stories, one about forests and then one about more of my midlife crisis farm research. Okay, so like many of us, I also went through a midlife crisis, and this is what led to the more ag research. But the essence here is that we're trying to develop new ways to look at especially remote sensing data by using simulations. The catch being is I find myself in this environment, right? I work in imaging science, and what is imaging science? And I don't have my cell phone with me, but my department, it has this nice way, previous department, he always said anything that has to do with that camera on your cell phone, the collection of photons through the optics onto the detector plane, image formation, extraction of information from that imagery, displaying it, human visual systems, and so on. So it's we call it the imaging chain. It's sort of a term we've coined. I sit on the applied side of that. Our students come in with calculus, physics, computer science type backgrounds. They get great jobs at great places, like I guess Purdue students as well. But I've been really able to tap into a unique set of students, different than what I would have been able to do, say, at a Virginia Tech or a Oregon State forestry program. It's been a very interesting environment for me. I also had to adapt because I come from forestry, hardcore forestry, and I had to adapt. So we've been using cartoons, and you can lie with cartoons, right? I stole this from Flip Phillips. He was part of this Pixar team. He's now in motion picture science at RIT. I've never seen this movie, but I think it's Inside Out, and this is Joy. And the idea here is you can see all the movement Joy is making, right? These are things that are not humanly possible, but none of it really bothers us because it's a cartoon, and you can see the animation behind it. And that's sort of what I want to convey here. I go to a NASA meeting, and I talk about our simulation system, and you see people roll their eyes because you can lie with cartoons, right? So we go to great lengths to make sure our cartoons are physics-based, that they're viable, and they reflect the truth and the physics you would expect in a forest environment as photons propagate through the canopy and scatter through the canopy. So that's just something I want to mention up front. We use this tool called DeerSig, digital imaging, remote sensing image generation. Not very, I would say, creative, but that's what it's called. DeerSig is a very unique tool created by a guy called John Schott. He's pretty famous in the Landsat community. Back in the 90s, he got together some strong physics, computer science students, and they came up with this kind of tool that could allow you to build the environment that you're sitting in now, essentially. They can extract the pure geometry of all the chairs, the carpet, the desks, the people, then attribute it properly with spectral and emissive properties. And now I have a physics-based environment that's geometrically accurate. And you can think where I'm going with this probably, but I can now simulate what any given sensor would see. I can now develop algorithms in an environment that I can manipulate, that I can create truth data, label data for machine learning algorithms, for instance. So that's one big thing that we're doing. But this sort of slide, this sort of shows the concept of DeerSig. We're on the very left. We use tools like Onyx Tree. Onyx Tree is famous for Lord of the Rings trees. Okay, that's their claim to fame. We use Blender a lot. We do field measurements of plots like we used to as foresters. And we use all of these tools to build this geometrically accurate scene. And as I said, we associate the right optical physics-based properties for that scene into our sort of, call it engine. And then you can start programming any conceivable remote sensing platform. It used to be more optical based, optics, hyperspectral, RGB, but we've since added waveform LiDAR, discrete LiDAR, even flash, as well as SAR. It's now also an ability that the DeerSig team have built in. And now I can simulate a scene. I can simulate waveform LiDAR. And I can extract, I would say, reasonable, for the scene anyway, very reasonable, accurate representations of that scene. Do we claim the scene is absolutely true to nature? No. It's physically impossible to measure what is so complex out there, so variable in nature, and represent that perfectly in the scene. So we do acknowledge that. So it's a very simple process, Monte Carlo ray tracing type. We cast rays into a scene. We look at the transmission, the scattering, reflectance, absorption. That creates a photon bundle path, right? That gets mapped onto a photon map. And that gives me my ultimate scene, where what you see on the right is not a real scene. It's actually a RGB rendering of a cartoon forest. But it looks real, it feels real, and it acts real. So that's really important to us. So it's important that we also incorporate not only the system noise, but also the atmosphere. So we use Motran to model the atmosphere, so we can aggressively model that. As a matter of fact, DeerSig was used extensively. I was just mentioning this over lunch, but for Landsat 8 modeling. Before USGS and NASA even launched Landsat 8, DeerSig was used to map out the detector plane, because it has sort of these weird offset detectors for redundancy purposes. So Landsat 8 actually collects its image not in a frame, but in sort of overlapping frames for the different bands. You and I see the beautifully processed imagery, right, from USGS. And they also wanted to say, listen, if I use an active cooler for my thermal sensor, what kind of jitter is that going to add to the system? So John Schott and his team could actually model Landsat 8 and tell the USGS, this is what you can expect as output, and this is what the impact of the active cooling system is going to be in terms of system noise. So it's been used quite a bit, published heavily, and I'll be honest, I'll say this cautiously, but it's extensively used in the defense industry, to the point where at some stage, L3 Harris said, oh, we want to fund DeerSig development. And the government said, And they wrote the DeerSig team, not me. They wrote them a check and say, you develop the next generation DeerSig. We don't want any one company to own this. It's not open source, but it's freely available. Only requirement is that you attend a training session, which I think costs a few $1,000. But then it's yours to use. So anybody out there in industry, government can use DeerSig freely. But obviously they don't want you to get under the hood and mess with all the mechanics. So two stories. The first chapter of story one, starting with small cartoons. So I arrived at RIT in 2008. I heard about this thing called DeerSig, and I scoffed. And I said, I'm an empiricist. I measure trees. Right? Why would I fiddle with cartoons? But I thought we'd give it a try. And my first student, William Wu, brilliant student. He helped develop some pre-processing chains for waveform LiDAR especially. At that stage, we were working actively with Greg Asner. Some of you might know him. He's like a rock star in our world of remote sensing of the environment. And one thing that our team in South Africa couldn't really contribute to Greg Asner's team at that stage at Carnegie Institute for Science was waveform LiDAR processing. So we said, we'll tackle that at RIT. So William was the one who looked at deconvolution of these waveform signals. So if you model a received waveform system as the convolution of the transmitted pulse, the actual cross-section of the target, and then the receiver impulse response function, you can deconvolve, untangle the instrument's impact as well as the outgoing pulse shape and actually reconstruct the real cross-section of the target in theory. But you have to look at potential deconvolution approaches, right? So how do you validate this? How do you determine what the best deconvolution routine would be? So William built tiny little trees. And you can see an example at the top left there. And he simulated waveform systems, Greg Asner's system. We could simulate different outgoing pulses. We could simulate different impulse response functions. And he essentially determined that, listen, of the options, Richardson-Lucy, Wiener filter, non-negative least squares, Richardson-Lucy performed the best. He could compare the actual deconvolution outputs. This is a little blurred, so I apologize, but he can compare the actual deconvolution outputs to a truth data set simulated with 2 nanosecond outgoing pulses, very crisp pulses that gives you a very detailed target. You can say which one of those deconvolution routines gets me closest to that truth target. So you can see where this was going. And so we established this sort of processing chain. Why? We wanted to model woody and herbaceous grass biomass in a savanna ecosystem in Africa. That's what William did for his PhD as an imaging science student. He's one of the best students I ever had. He went on to work at Apple's iPad display unit, and he's high up now. But that's imaging science. I was telling someone earlier, they're like computer scientists. They become tool makers in imaging. So they can go work at medical imaging firms, even if they've done a remote sensing PhD. So William said, well, let's look at a processing chain for this woody biomass estimation. You have a received waveform. So here you have intensity as a function of range or time. And if you sort of squint, you can see a little bit of squiggliness right here, sort of high frequency noise. So we first put it through a frequency filter, a Fourier transform, and we filter up that high frequency noise. Then we have the final received waveform. We look at the outgoing pulse, which is sort of Gaussian, but it does vary a little bit. So you have to grab every outgoing pulse from the system to do the proper deconvolution. And then the system's impulse response, when you ask Optech and these folks, how do you get that? They say, well, you just take the LiDAR and you point it at a wall and you get that crisp impulse response from a hard target. How do you do that if they don't give it to you? We not simulated, extracted these from Lambertian targets in the scene at nadir. So we would always pulse the nadir pulses for Lambertian scenes in this specific target area, which was Kruger National Park in South Africa. So this is our extracted impulse response. And then finally, that's the deconvolved waveform. And you can see it looks very different from the received waveform. But now I can see that there was potentially 2 specific interactions. For the record, Greg Asner flew a pretty broad outgoing pulse at that stage. I believe it was 16 nanoseconds, which is very broad if you think about it, because he wanted to penetrate through tropical forests and so on. So the system settings weren't ideal for a savanna type environment that you can sort of see in this little area here. So we looked at things like elephant damage, herbaceous biomass, woody biomass, etc. Keep track of time. So this is an example of that savanna scene, and you can sort of visualize, this is not from our papers, but you can sort of visualize a waveform interacting with a canopy, some sub-canopy, and finally the ground. And then you can sort of visualize it in voxel form if you associate intensities with voxels. We've all done this, so this is nothing new or special. The quirky thing we saw, and we saw this in Deersig first, we saw these under the ground returns, below ground pumps. Okay. For those of you who've worked with discrete return LiDAR, one of the first things you do is you classify ground returns, right? Or you get that from the vendor. You interpolate the digital elevation model and you normalize the returns by height. And inevitably, you get negative residuals. Those few returns that look like they're underneath the ground surface. What do we do with those typically? We zero them out, we throw them away. System noise, interpolation artifacts, etc. But we saw, if you look at this carefully, this is a deconvolved waveform, and you can obviously decompose it into two Gaussians. We saw this little bump. This is the ground. So again, intensity or radiance, if you will, as a function of time or range. This is the ground return right here. And then there's this delayed return below the ground, which, believe it or not, in many instances are associated with stuff just above the ground, like coarse woody debris, herbaceous biomass, grass, thick grass. Now, the savanna grass, pretty thick grass. It's not like the grass we have in our lawns. So we could sort of hypothesize, even in deer seek world, we see these delayed returns. Are we throwing them away, or is there signal there? And we decided, let's try it. Let's try and model, things like typical things that you extract from away from LiDAR, height, ground width, etc. But let's also see if we can relate the decomposed waveforms below ground return to herbaceous biomass. Now, don't get me wrong. It's not like you're going to start applauding because it's an R square or whatever. This was an R square days, right? But there's definite signal there. And I was just talking to Songlin earlier about Mary Arthur down in Kentucky. She was interested in modeling coarse woody debris levels for fuel load. And we could also associate discrete return negative residuals to the coarse woody debris right above the ground. Typically, signal that we would throw away. And this, I'm sort of trying to convince you that we actually saw this in DRC. And then we saw it in Greg Asner's data. We saw it in NEON, National Ecological Observatory data. And William went on to model, I don't know, tree height's the easy one, woody biomass in the savannas, foliar biomass, etc. in the savannas. Published these papers, went on to work at Apple, and I said, William, it's not only one paper. Let's have some fun with this one. What if you simulate a tree and reconstruct it? I want to be able to, and hopefully you can see the thread here. I want to be able to take LiDAR data, scan a forest, and then build my own virtual environments for simulation purposes, as opposed to building trees and placing them where I think they should be, how tall they should be, the kind of interaction there should be, etc. I want to scan trees, forests, and build my own virtual scenes so that they're even more realistic. So we tried this eventually, just with virtual data. So William tried leaf on, leaf off versions, all simulated, use some morphological filters, could detect the center of the stem. So that's the stem lean angle for that specific troop geometry. And then using simple clusters, published clustering algorithms, extract the branches and say, here's your first order tree, all from a theoretical simulated LiDAR tree. But in theory, this workflow should apply to any tree that I scan with a dense, even discrete system in this case. So that's where we were sort of targeting, where we're going towards in a sense, is trying to say, listen, how do we build ever increasingly accurate scenes for even more accurate simulations? And hopefully you'll see the thread and the method to our madness here. So we took a first step. We said, let's take Harvard Forest in Peterson, Massachusetts. You're probably all familiar with Harvard Forest. It's one of the most studied, I would say, ecological forestry sites in the country at least. And we used some inventory data from them and built this plot. Different species, oaks and maples. Paul Romanchek did that work. And Paul, amongst other things, this was in the day when computational resources weren't what they are today, and probably won't be what they are in 10 years, but said, what is the least amount of geometry that I need to get an accurate signal? So Paul did a lot of playing around with saying, I'm just going to float leaves. Just keep the leaf facets object. I'm going to add some light first order stem / branching. Then I'm going to add some increasing second, third order branching, and maybe even later the little stem or the leaf petioles. Long story short, 95+% of the signal, as you can imagine, at 1064 nanometers near infrared for the laser, driven by foliage. So Paul was able to show, and you sort of see different branching levels here in the legend, leaves only, but 95% of the signal and the truth driven by foliage, which is sort of a expected outcome. but we could prove it conclusively in this environment. And then we could actually distill our original scene that at that stage was about, I think it was about 500 gigabytes. We could distill it down to about 50, just because we could remove so much geometry and still claim that we're accurately representing the signal interactions. So that was sort of part of our, let's call it untangling of signal in context of limited computing resources. So there I was, and we said, oh, we want to build better scenes, right? So here's chapter 2. We're moving on, and this whole saga, I think, of forest cartoons. I was very privileged to work with this guy. He's sort of grayed out here, Dave Kelby. Very, very smart scientist. We don't work at Oak Ridge and elsewhere. And at Paul Coppin, if you know Paul Coppin, he's an interesting character. I learned a lot from him. Things we were having this discussion earlier, Melba and I, but one of the things that his team did is they integrated a very affordable SICK LiDAR sensor, literally SICK, it's a German company. This scanner, I think the application it was primarily designed for was for port scanning. It literally just sits there and sweeps in a 270-degree arc as the crates come by, and they just measure the dimension of the crates and so on. So we put it on a rotation stage. And that stage, this was actually work with Mary Arthur. So we had the motherboard in a Pelican case, a car battery in another Pelican case, all wired. It was an ugly affair, traipsing through the woods and the bramble and so on. But you could collect a 270-degree scan by 360 degrees in less than 30 seconds. So it was a very affordable, practical, operational scanning system. And that was its I would say, attraction to me, because I from an early age, growing up on a farm, doing forestry, and now working with farmers, and you are very well versed in working with farmers, they're pragmatists. If you show them a $250,000 scanner that requires a generator and a half an hour to collect all the point clouds, they lose interest. But if you show them a 30-second scanner, yes, it comes at a compromise, and I'll show you that in a second. Suddenly they're interested, because this is a potential true inventory tool. So we were scanning at Aardt Forest, and some of you know Crystal Shaw from UMass Boston. Crystal and her very good computer engineer, Francesco Perri. And Francesco Perri, as you can deduce, is Italian. They make Ferraris, right? So he looked at our system and said, I can do that better. I won't try and do the accent, but I can do that better. So Francesco came up with this idea. Same sensor head, Arduino system, the Walt battery pack, totally wireless. And this whole unit is so compact and robust. I've had it in Micronesia, in the middle of, I don't know, very far away places, in mangrove forests and rain and tropical downpours. Very robust. Again, 30-second scan time, about 4 hours per battery. And it's just grown in application from there. So now this is what the system looks like. It's much more, I would say, elegant than that original. We call it the Crystal wanted to call it the cute biomass LiDAR. I said, please no. So we called it the compact biomass LiDAR. So here's some specs, and here you can see our LiDAR specs, and you can sort of see why it's cheap, why it scans fast, things like the beam divergence compared to some of the then industry standards, very large beam divergence, very coarse angular resolution, but again, 30-second scan. And in a forest environment, it's pay dirt. If you can scan in 30 seconds, move to the next block, 30 seconds, move to the next block, you get the idea. As opposed to regals and optics where you have to sit there and wait in windy environments. So you cannot sit there and wait for 15 minutes with all that's going on. Just to put it in context visually, so this is an Andreo projection, you know that drill where you sort of fold out the scan, 0 to 360 at the bottom, and then the zenith on the y-axis. And you can see in the bottom left is our scanner to scale compared to a Faro, then Photon 120. It's now progressed in the technology. You have to sacrifice a lot for that scan time and detail, but you gain a lot in the compactness, the robustness, and the scan time. But that's something you have to, I would say, settle. You have to realize that. So what did Dave Kelby do? Dave Kelby was tasked with the scene construction and forest inventory, like many of us have done. Phil Radke at Virginia Tech, Some of you know Atticus Stovall at NASA and folks like that. So Dave came up with a unique approach. And I asked him, I said, listen, I don't want to use tooling balls, these polystyrene balls, to register my multiple scans. I want us to do this automatically, So Dave said, okay. He would extract the stems as cylinders, very accurately so. In adjacent scans, he would intersect the stems with a digital elevation model. And you can see probably where this is going. Then he would try and find the overlapping geometries of those intersections into adjacent scans and do sort of a pairwise marker-free. So you don't need any targets other than the actual natural targets seen. And he could register 25 scans very accurately in this manner. So there we go from the occlusion drawbacks of a LiDAR scanner where an object would cast a LiDAR shadow behind it, to actually being able to move the scanner around in the scene, automatically register it, and now have a comprehensive representation of the forest scene. And if you use your imagination and tree growth forms, you can actually grow this concatenated point cloud in something resembling an actual forest out there. Because think about it, you can also extract LAI estimates from the LiDAR. So if you know what the LAI should be for any given scan or location, you can propagate that thinking through the canopies until you match that LAI estimate. So now I was hoping we're getting to a stage that we can go scan a site and I can potentially extract a real forest environment for our simulations. Just a little bit STEM modeling for those of you interested in this. It's basically a ransack type approach, but it worked really well looking for the curvature of the stems, and it was pretty accurate, even for a singular scan. But I think many of you have been working on things like this for a long time now. And they sort of use these different no initial pose estimates, no markers required. And he used sort of a graph theory approach where you would look at, this is just an example for 2 scans. Obviously, you sort of see the one set of trees from the one, the other set of curvature for the stem from the other scan. So you think of scan 1 over here and scan 2 over here. And they've essentially sort of set up a network of overlapping similar geometries. And then you could recursively trace the path to any given scan in my 25 scan set to find the lowest cost in error traversal of those scans set to make sure that I get the lowest error in my final registration. So he was a very smart student. He was one of those PhD defenses where you say, what just happened? He's really smart kid. So Dave really helped us expand this to next levels where we can actually extract forest environments from multiple scans like this. However, you go to Hawaii. I was telling someone I got to do my sabbatical in Hawaii, actually with Greg Esner's lab there. And it didn't work at all in these Hawaiian forests because you have ferns and stuff underneath, not nice, clean Harvard forest, deciduous type environments. So we're still working on some more complex forest environments. So the first of the 2 stories, I'm sort of going to conclude by saying what the next generation is. This is really exciting for me anyway. But it's not there yet, and then you'll see why in a second. So when we started to think of larger forest areas, we wanted to make sure that our physics-based modeling, especially in something that is not often looked at, the forward scattering component was accurate. Everybody knows what BRDF is, like bidirectional reflectance distribution function. In other words, how an object reflects inbound light as a function of light source and observer geometry. So a lot of people have worked at satellite imagery, airborne imagery, and so on. But it's surprisingly few forward scattering, transmission distribution functions exist. And we wanted to be sure if we trace laser photons, especially at 1064, through a forest canopy, that radiometrically speaking, we're making the right assumptions on how it will forward scatter. So a very smart Air Force student, Ben Roth, he did his PhD. We have I think like Purdue does as well, right? You have access to Air Force officers and so on that do their grad degrees. And they're typically the most productive, most focused students that I've ever worked with. They are very focused, as you can imagine. The best of the Air Force, I guess. So Ben published quite a few papers on essentially modeling the forward scattering mechanisms, the transmission scattering mechanisms in forests. And he did this using a goniometer. This is Chip Bachman's. Dr. Chip Bachman used to be at the Naval Research Laboratory, came to RIT, and he built 2 of these. Very cool instruments. They're field portable. You could put a target in the middle of this, and then you have a camera arm. There you can see the sensor. So you can sense, as a function of inbound solar illumination angles, you could sense the target's BRDF. And all Ben did is he adapted this system to actually be able to look at the transmission for its scattering. And he just used maple, sweet gum, and oak type leaves to do that. And this is sort of an example of, this is, I think, the observational illumination angle, and these are the observation angles at on the circular frame here for different wavelengths. He sort of looked at how what that distribution looks like as near-infrared energy propagates through a leaf. Because we wanted to do big things. We wanted to simulate large forests, and we wanted to be sure that the physics, the radiometry were sound, behind all our simulations. Long story short, sort of summarized at the bottom, Lambertian is fine. It's a lot of work to actually just say a Lambertian assumption. In other words, even scattering forward, especially at big footprints, and near-infrared is actually perfectly fine. It falls apart at very small footprints and visible. So 532 type nanometer lasers. Lambertian is not necessarily the assumption you want to make. But for our purposes, 1064 then showed that it's perfectly fine. And here you can see Lambertian, different mixture models and forward scattering models. And he said we can continue with Lambertian. So that brought us to Aardt Forest again. Remember, originally we had I think it was a 40 by 40 meter plot-based inventory site. And this is where Aardt Forest is located, for those of you who don't know. It's a little town called Petersham, Massachusetts. A lot of active research goes on there. And very interesting site. And we decided to focus on something we now call the mega plot. It's about 500 by 700 meters in bounds. So it's a pretty large plot, even in terms of hectares, it's huge. It's very well documented. You can see some of the neon plots. If you're familiar with neon, these are the actual sort of neon plots that they've established in this mega plot site that we have identified. Here's the big neon plot. So they have 40 meters and 20 meter type setups and 10 meter plots. And then there's always some ecologist or forester doing research at Aardt Forest would actually have forest plots, like fixed plots or variable radius plots and so on. And you can see, so this was very well, let's say, documented, but we wanted to go full on. We wanted to use neon AOP, airborne observation platform, which now flies the next gen Avras at 5 nanometer spectral resolution. And we decided we want to use neon data, inventory data to build a virtual scene. And on the left, you see the real, and on the right, you see the virtual simulated scene. Does it look exactly the same? No, it doesn't. It's almost impossible. It's as hard as you try, unless you have a STEM map 500 by 700 meter extent, it's almost impossible. But our core intent was it should look the same sort of, but also feel the same. So we measured LAI extensively through this whole site, AccuPAR as well as terrestrial lasers. We measured the spectral data quite extensively. So material properties were collected. We used prospect cell models to forward model sometimes, backward as well. We collected over 100, I think it was 125,000 individual objects. That's not facets, that's physical objects, each with their own, thousands of facets of different species. Rob Weibel was another Air Force officer. He's another Air Force officer. He needs to defend the semester. But he has all these trees that he built and assessed. And now we can actually simulate that Aardt Forest scene using, for instance, Neon's platform. Here you can see the push broom spectrometer, Avras Next Gen, as well as the waveform LiDAR system. So we now have simulation capability and validation capability for the scene. So we can compare apples to apples. This is what the virtual scene looks like on the left. And I mean, if you know it's virtual, sure, you could probably pick it apart a little bit. But if I didn't tell you on the left, you were looking at a virtual scene and you couldn't see the bounding sort of artifacts, it looks very real and it feels very real. If you zoom in on the left here, I've got virtual, and on the right, I have real. Again, it's not going to be perfect, and I think we'll be remiss not to admit that it never matched nature perfectly. There's a sort of a swampland over here that we're trying to get even better and better. You can sort of see it here in the virtual data versus the real data. And Rob placed a lot of man-made targets on the forest because that's part of this project. Is we want to see what are the required system parameters, collection parameters to properly sample the understory. We're so focused on canopy structure, etc., but some of the funding agencies want to look at target detection underneath the canopy. What should I be scanning? How much should I be scanning? What should my flight parameters be? What kind of algorithms can we develop? And here's just some examples. Again, on the left, you've got Aardt for spectral data. I believe these are actually in situ ASD type data, and then simulated spectra. Again, it's not going to be a perfect match, but we want the physics to be right. We just want the physics to be right so we can actually do the simulation afterwards. So now we've been using this as part of sort of ongoing work where we have on the left is the virtual scene, and we can collect truth data. And you can imagine the sky's the limit in terms of truth data. If I voxelize that scene, I don't care if it's 0.5 meter voxels, 25 centimeter voxels, or meter voxels, I can now collect labeled truth data. What is in each exact voxel? I can go to the detail of leaf angle distributions. For those of you who've measured leaf angles in the forest, you know how complex that is. Here, I can manipulate that, sure, artificially, but as long as I make sure that my leaf angle distributions are matching published distributions, I'm good. But I can now start manipulating leaf angles, and I'll show you a quick example. It's again ongoing. It's NASA-funded work with actually Chris Goff and not Phil Townsend, just a ecologist in New Hampshire, Scott Ollinger. Some of you might know Scott Ollinger as well. So we're working with him on that as well. But we can generate thousands upon thousands of labeled voxel level. We can look at voxel content, how much leaf, bark, open, ground, man-made targets. We can look at voxel signal, because you can imagine you might have a content type that dominates the voxel, but the signal might be dominated by something else in that voxel just because it's 1064 nanometers. And now we can start to do predictions, classifications of voxels. So this is where I lose the plot when it comes to machine learning. I'm not a machine learning expert. My students and some collaborators are. So some of you might notice or recognize all the lingo here. But we essentially use a 3D CNN, which apparently is now the, I don't know, next best thing since sliced bread and so on. And you can sort of look at how well can I classify. Pretty simple. So I'm looking at leaf, bark, it calls it background, but it's actually sort of called an empty space, ground, and objects. And you see pretty good recall and precision rates for most categories. Not all, but most categories. But it's something that we're continuing to refine. If you see this, for instance, ground sort of in the brownish, here's some brush. Here you see the bark / stem, and you see the foliage. But you can maybe see the implication here for some of the work like what Brady is doing with Chris Goff, and they call it rugosity, where they're looking at the under canopy variability in structure as well as the top canopy variability in structure. Because talking to these forest ecologists, apparently rugosity is a bigger explanatory variable or driver of NPP, net primary productivity, than many of these other traditional variables that we've traced that we've been measuring over the years. So if we can measure rugosity from space, there's a whole slew of opportunities that will open up. And Keith Krause at Neon, he's been working on mapping occlusion effects. So you're looking here at a forest. I think this is actually real data, a forest, and you can map in black the occluded sections of that forest. In other words, areas that went unscanned. Now, as a forester, you as a forest ecologist or whatever your trait is, if you want to characterize a forest and that much of the forest went unscanned, how can you hang your hat on any type of trait assessment? So we want to characterize exactly where that level of scanning is. How can we improve that scanning? What kind of flight optimization can we apply? And conversely, at the bottom, you're looking at transmission voxels. So this is a different scene almost, but you're looking at voxels that were truly empty and went unscanned. So if you up the scan rate, angles, overlap, you say, okay, now I can say which voxels should truly be empty. Again, think, I'm not saying nefarious purpose, that sounds horrible, but if you want to know about objects underneath the canopy, you want to know is there truly not an object? Or did I not detect an object because I didn't scan? That's a very important decision point, I think, for any type of 3D scanning. And then finally, on this specific topic, this is just a simplistic rendering. So Kedar Patki is doing his PhD. He's working with Scott Oliger's team out in Harvard Forest and elsewhere, where he's actually trying to see what impact does leaf angle distributions have on forest structural trait assessment. So he's varying leaf angles using established published methods to look at things like leaf area index and other type of traits, structural and spectral biochemical type traits, and seeing, number one, is there impact? Number two, if there is, how can we mitigate? How can we adapt our algorithms to not be so sensitive to leaf angle distributions? So it's a toy. I think it's a fun toy that we can use for this. So in the last few minutes, I'll just talk briefly about my midlife crisis. So I went through my midlife crisis, and like many guys, I bought a V8 Mustang, which I still love very much. Really, it's a joy. And I got stuck in my forestry research. I sort of said, I love forests. I mean, that's what I was trained in. But I felt like I was publishing papers that I shelved and I wrote up on my annual report, and I was worried that no one's really using these papers, right? But a farmer, if I can put something in a farmer's hand, that would really be rewarding. So that's my midlife crisis. And that coincided, as I mentioned, some folks with Aardt starting to invest in, let's call it expanding research areas. And our group won one of these awards, and we decided to use it for drone development, UAS capacity development. We were way behind the curve. Melba has been doing drone flights for I don't know how long.
You make me sound old.
No, you're. I'll put it up. She's a legend, right? I mean it sincerely. She's been doing drone flights and hyperspectral assessments since Texas days, I believe. Pablo Zarco Tejada, many of you know him. He is famous in Europe. I think he's now in Melbourne for doing this way before many of us even thought about it. You know, so I won't claim we're in the front of the choir. What we're trying to do well is the imaging science component of it. Aardt is in upstate New York. For those of you who haven't been there, Rochester, New York. Its claim to fame is that Bausch & Lomb, Kodak, L3Harris, a bunch of these kind of imaging companies, optics companies are based there. You know, so it's pretty famous for that kind of optics nexus, you know, and so on. But where was I going with that? I lost my train of thought. But long story short is Aardt is sort of a small fry when it comes to anything related to forestry or agriculture. The Purdue in our environment is Cornell, as you can imagine. And here's the interesting thing, Cornell doesn't do a lot of imaging. I don't know why, and shouldn't tell them anything about this because I'm worried that they might do it. But we have wonderful collaborations with them because I work with, you know, agricultural pathologists, corn agronomists, viticulturists, and they don't know anything about imaging. I don't know anything about winemaking and wine growing. So it's extremely, I would say, fruitful, fun collaboration. I love working with them. I hope they do too. But we keep writing proposals and doing fun things. So working with Cornell, we've been working on a bunch of different topics. I think I'm preaching to the choir, but I'm just going to say it. So I go to upstate New York and I visit Peru. I got the privilege to do that. They want the same things, it seems, farmers. As I said, I grew up on a farm. My dad was a vet, so farming was more of a hobby, but yield forecasting, either for in-season adaptation, mitigation, but what we found is more for logistics purposes. People want to know labor, processing, how many trucks they should get, etc., from which grower, okay? Disease detection or risk prediction, depending on the disease, right? And then finally, a harvest scheduling, which was a strange one. So in upstate New York, they know their beans will mature between 50 and 56 days after planting, okay? But when exactly should they harvest which field? And if you think about it, which portion of a field, when the beans are a specific sieve size. In other words, they optimize their yield. You go to Peru, guess what? They want a harvest schedule, avocados. When should I harvest avocados so they can make the trip across to the US to your local grocery? Okay, so similar problems, just different places. So we worked with the USDA down in Beltsville, Maryland. We flew our just simple mica sense at that stage, also hyperspectral. We were there when the specific overflights for different platforms happened. We had cal panels in the field and everything. with the core intent of being able to do this. This is Grady Saunders, one of the whiz-bang nerd research staff in our group. He built this procedural model working with Corinne Ketterings from Cornell, where he could instantiate corn plants as a function of growth stage, V2, V4, etc. And then, attribute the soil, attribute the plant, and long story short, build you a cornfield that is actually true to reality, to the point where if you look at the real imagery and the simulated imagery, you'd be hard pressed. We looked at the distributions, sure, they're not perfect, but they're actually very close. And Grady can now turn knobs in terms of irrigation needs, in other words, water stress. He can look at different stages of nutrient stress, etc., and just general canopy closure, LAI. We can simulate all of this, and very accurately so, physically very accurate so. And again, I'm not the guy who builds this, so I'm not bragging for myself here, but the neat thing is now we can ask some very interesting questions. And we're working with Corinne quite a bit on this, another Air Force officer. What does the ideal spaceborne system look like to map corn yield on a global basis? Now there's folks, Tenkabile, all these folks who've been working on these kinds of problems for a long time, but what they have at their disposal are just the resources in space at the moment. So if NASA were to develop the ideal space-based system to map corn yield, you can think of implications. You can look at political instability across the globe. You can look at future markets, et cetera, et cetera. What does that look like? And we can now take a scene like this and really toggle the switches, instantiate nutrient stress and variability in nutrient levels, instantiate LAI variability, et cetera, and say what kind of detector at what spatial temporal resolution can resolve all these variabilities. So that's also ongoing work. And then I'm close to being done here. I know it's a mouthful, but so more of the actual research going on with Cornell. And I thought this was going to be a cool slide, but listening to everybody this morning, you say, oh, sure, we'll fly these too. It's a lot of fun, right, working with a drone team. I didn't build this drone platform or stand up the drone team, so I cannot take much credit. It's very typical, I think. Many of you in the room will say, yep, check, 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 check. We use these. I think one thing that does make this unique is a KU band SAR. Not on the same platform. Someone asked this morning. We typically fly 3 platforms. The workhorse is the one you see there, and you all recognize the trees. That has the Velodyne, the Nano, Headwall Nano, the MicaSense, uncooled bolometer, uncalibrated in other words. Then we fly a calibrated FLIR. It's accurate to the precision is what, 0.1 Kelvin, I believe. It's really very, very nice calibrated system. And then on yet another platform, we fly the SWIR because it's a cooled system. It's a little heavier. And then yet on another platform, we fly the SAR. And I don't do the SAR research, but a lot of folks are interested in, you can get soil moisture, things like that, and so on. So it's a pretty extensive array of imaging. And we spend a large amount of time on calibration. And this morning's meetings with many of you have been really eye-opening because I can see immense ways that we can work together and learn from what you've been doing in terms of GCP list registration. We still use arrow points to register our scans on our images. We very much are working hard on robust downwelling, instantaneous radiance measurements, so we can go away from cal panels, because that's a big constraint, just pragmatically speaking. And so there's a lot of things. And this is my pitch when I go to a farm. So with Cornell, they have a huge extension arm, probably like Purdue does, right? And you go to a farm day and you fly your buzzing $250,000 drone, and my chest is just pounding with pride, you know. And the farmers ooh and ah was it, you know, what it sounds like when it takes off, and then they lose interest. It's bizarre. They start talking to each other about the family and the crops, and I think why? Because this thing is flying at 2 meters per second to integrate enough photons for high signal to noise for the spectrometer. They look at that super duper drone and say, that cannot cover my farm. They think extremely pragmatic, you know. You fly the unsexy $10,000 drone, zipping up and down. Yeah, now we're talking. It's only a multispectral system, and it costs what, $8,000 or $10,000. But it can cover 100 acres in less than an hour. Now suddenly they're interested. So we've really been pitching this idea of the Goldilocks principle. We overdo things on the left. We collect too much spectral, too much structural, and we acknowledge that right up front to identify the exact solution for any given application. So that's been a key thing. Working with Sarah Petibridge at Cornell, white mold is a big issue, and snap bean. White mold has two key characteristics. It enters the plant through the flowers, and it likes a nice closed canopy because it's nice cozy in there. It's like a greenhouse, you know. So if you can measure those two things, if you can assess flower intensity and you can assess canopy structure, you can feed that into a risk prediction model for a service provider to use. So you want to optimize this one axis, right? True negative and true positive. You don't want to spray when you don't need to, and you definitely want to spray when you had to spray. You don't want to waste money or impact the environment negatively. So Ethan used this study. He used the oversampled data set to detect flowers. Now, as you all know, these flowers don't point up at the same. So you can count the little white flowers. It's all a physiological response at the canopy level, just like you and I getting sick. Both of us might look exactly the same, but you point a detector at once. You wait a minute, fever, COVID, maybe, I don't know. So Ethan said, silicon range, these 6 bands give me a 94% accuracy in flower intensity detection. There's one checkbox, right? The neat thing, and as many of you in the room would probably acknowledge and know, silicon, it's cheap. Sure, I can do a heck of a lot with shortwave infrared, but it's not ideal if I find my solution in the shortwave. If I can find it in a 5-band silicon sensor, which I can filter very specifically, that's pay dirt. So we actually met with a company, it's a new startup. They do thin film development. And the idea there is that you could essentially develop filters on an application-specific basis. So if I have the 5 silicon detectors and I can plop on a filter for my nitrogen flight today, calibrate before I do that. But tomorrow someone contracts me to fly for irrigation scheduling. I put a different set of filters on there. And I fly the same system, I just filter for different wavelengths. So it's very much a theme that we've been chasing after. And here's literally the last 2 slides, but so Amir Asanzadeh, he's also another smart student. So it's sad sometimes I was smarter than I am. So like, Amir was tasked with classifying different sieve sizes for snap bean, and I think the sieve is actually behind there. You cannot see it really, but so if you know the crop scouts, they have this little ruler with indents, and they physically go to a snap bean field and they measure the little bean pods. And say, no, it's a sieve size 2. It's not really, or it's a sieve size 5 or 4. Yeah, we probably should start thinking of harvesting. So Amir was able to lump these 2 large sieve sizes into one category and get pretty accurate, close to 80% accuracy, without stepping a foot in the field. Now, if you can start expanding on that, it's pay dirt. Now, don't get me wrong, when you go to, we work with Seneca Foods and Farm Fresh First, with a few agricultural industry partners. They say, well, can you do this from space? Because I still have to visit the field with my drone, right? But imagine if you could sit behind your computer as a manager, is up field 7, 19, and 20 needs to be harvested tomorrow. And then I'm going to optimize my yield. That's a big deal. This was greenhouse. And Melba and I had this discussion this morning. Worked in a greenhouse. So we flew the next summer with Cornell. And here you can see that same classification on the x-axis. Sieve size is 1 through 4, lumped as one class, versus sieve size is 5 and 6. And even better, I don't know why, better accuracy than the greenhouse. So it actually scales really well in determining when exactly I should harvest. Now, maybe one day we get at that kind of mechanization where you can not only say I should harvest that field, but maybe you can even get, if it's economically feasible, to harvesting portions of fields on different days and allowing certain sections to even grow another 2 days for yield purposes. So it's a very interesting field. But I know that this is what Purdue does well, amongst other things, is ag. And so we're very much scratching the surface here. It's been, as I said, a very rewarding collaboration with especially Cornell and others. So yeah, that's sort of what the story I wanted to tell you, where we're working at in the simulation field and some of the ag research. I wanted to balance a little bit of forestry and ag, but I'll be happy to take any questions. Hopefully I didn't go too long. Yeah.
All right, well, it's open for question. I'll start with one. This is a fascinating also. A lot of cool ideas. I have one concrete one specifically relating to your co-registering of these support tree stems using geometry so you can match. Are you guys doing this sort of on the fly or post-process?
I was post-processing at this stage. Yeah.
Okay. And does it make the computation 100%?
Not anymore. It used to be pretty. I mean, this is now pretty dated research that we're trying to revitalize now because we see the need for these kinds of scene development. But at that stage, I wouldn't say it took long, but it was still required post-processing from the native format to other type of ingestible formats, running the code. And it's MATLAB code, so it's not very commercially, I'd say, viable. But yeah, now it's not too bad at all. It's actually pretty fast. I still think in-scene targets are probably a little bit more accurate for obvious reasons, but this works very well otherwise.
So, I've always lived in admiration of RIT and nursing as physics-based, modeling. And, now that I'm working in ag as well, then there's the biological piece of it. And so, there's a lot of these crop models but they're point-based, but they bring in weather, biology. I have two questions. Have you thought about or investigated any kind of, I mean, these models, as you well know, are like a tangled network of stuff, of integrating the two strategies? That's question one. Question two, as a non-biological person and more of a data scientist type, then, we're all doing, we laughed about this today, deep learning stuff. And so, but we know that it can only replicate and analyze what it has seen and do it well. Although we're beginning to now do simulations with GANs. Have you seen anybody trying to integrate these kind of strategies into the models that you guys are developing?
So I'll answer the second question first. I haven't really come across, again, I'm not a deep learning expert at all. I really am not. I sort of have a bunch of students who are really good at it and they can apply it, and we work with other faculty members who are way more knowledgeable. One day I said, okay, they want to do disease prediction. I said, okay, so I can provide you with the reflectance data and the training data for the disease. So, and I can also provide you with some transforms of the imagery. You know, the typical simple index-based and principal components and whatever, You guys said, I just want the reflectance data. The deep learning algorithm will figure out the connections and the transfer. And that opened my mind, it sort of blew my mind in a not a good way, because it essentially means that it will learn what it needs to learn to get to the end result, but you don't know how it got there. And I don't know of a lot of people that are exploring the mechanisms in depth. I think a lot of people are realizing they should, because the Tesla still crashes, right? So they need to understand the mechanisms better, even though they can claim that it's 99% true. 99% is not good enough if you miss a landmine, So no, I haven't really seen a lot of folks exploring. I think what DRC brings to the table is the ability to provide a heck of a lot of permutations of potential scenarios that you can claim at least that you're more exhaustive, as much as the model of the cartoon, as I said, allows for it. So that's interesting to explore, I think. And your first question was on, I should have answered the first one first.
Well, I was just, these are physics-based and the crop models are biologically based.
Absolutely.
And so there are ways of, integrating some of that.
So we were talking structure for motion this morning, and so if you can do structure for motion and negate the expense and processing needs of a LiDAR, and you've got your sensor that can detect the flowers and the snappy, now you can get a canopy model. Just from structure for motion. From one camera, you can get both things, right? So that's one big pay dirt. If I can get frame camera, structure for motion, I had a student who worked on Haiti earthquake data, and his task was to identify damaged buildings, and he came up with a very elegant, simple solution. He said, well, the typical roof structure looks like this. So if I fit the facets on both sides and I calculate the normals to those facets, you can imagine what the normals are going to look like on this side and what the normals are going to look on this side. As soon as the building is damaged by an earthquake, the normals do this. Similar principle we're applying to the SNAP-B. We're looking for evenly distributed hemispherical normals across the facet of a SNAP-beam canopy, or just jointed normals that indicates low risk for disease. So there you've covered the two remote sensing aspects. But you don't have to be a brain surgeon to realize that, well, this fungus is only going to thrive in high humidity, low wind scenarios, and there you bring in the meteorology. So you can embed all of that in the model. So that's actually Fei Zhang is the student, and Ruchi Gajar is a collaborator in India, actually. She came as a visiting scientist. They're working on a paper now where they're embedding all of this in a potential disease risk model. Because this is sort of a goal of us in this project. We don't want to rest until we cannot at least say, here is a heat map that someone could potentially use to guide their spraying of the crop. Will they? I don't know, but at least it's a step closer. So, yeah, obviously.
So this is first time that I get to know about this deer seek, and this is fascinating. And you did mention that this is still in development.
No, it's finished but constantly improved.
Okay, so that was my question. I thought my understanding is still in development. But what other kind of new features do you vision be trying to add into that?
It's a very dynamic environment. The DeerSig team is the best funded group in our group that have more money than they know what to do with, for both industry and academia. They're all set remote, ironically. They're computer scientists, physicists, and they visit fairly often. But to answer your question, if you work with the DeerSig team, they're very open to improvements. If you say, well, I really want to be able to do this kind of modeling with this kind of system, they can build that for you. It's a very dynamically, I would say, developing environment. As I said, it's free. It really is free. They do expect you to come to this training session. I want to say it's $3,000 for 4 days. So from an industry perspective, it's really not a lot of money. But they sort of want you to come see how to use the tool properly, and they've got models that they can make available, like this forest model. I don't mind sharing at all. More people that can use this, the better. And I'll be brutally honest, that is the bottleneck, is building an accurate 3D and physics-based model. That is the bottleneck. The actual simulating a Harvard forest scene of 500 by 700 on a just high GPU, not a HPC type system. It's quarter-meter voxels, so it's 25 centimeter voxels, takes 3 hours. So it's not even like it takes days to run a waveform simulation for a big scene, like relatively big scene.
The reason why I'm interested is because we have a task force where we accumulate a lot of data, like in Harvard forest. We can, generate 3D model like the Harvard forest using our data. So and there's a lot of student in each of the group who is doing individual tree segmentation, so that we can essentially count all those trees and potentially tree species information as well. So I think we have a pretty good database to build those kind of model for them.
I get really excited by like Brady's work and Chris Goff and Virginia Commonwealth University, the rugosity concept. It's so difficult to measure in field and verify. Brady has the backpack system that does transect LiDAR scanning up to the canopy. But in a virtual environment, you can essentially design the forest and develop a rugosity algorithm that works and then apply it. It's always good to validate it with real data, even if it's transect or plot-based and so on, just to have these spot checks, obviously. But it opens up a whole new opportunity for these kinds of investigations. I'm not trying to sell it for the record. I don't see anything from this. So I just enjoy it now.
Yeah, sure. So I have 2 quick questions. So the first one is a little bit technical. So you had this the rotating LiDAR, and you had a slide where you compared it to other LiDAR systems. I'm not sure if it's easy to do so.
Sure, I can see.
You are sure that this one is like doing, are you giving out anything actually by using this system compared to others? Or what exactly are you giving up by using this versus?
Oh, yeah, I went very quickly on that. I know which was slide you're talking. It's the main thing you sacrificing is beam divergence. So this is a pretty wide beam divergence. Let me just see. Sorry, I'm scanning it. There we go.
Yes.
Yeah. So the main thing you give up is this. I mean, just look at the angular linear beam divergence of these commercially very expensive systems range. This is a 80 meter range. I think at 90% reflectivity. It's a 905 nanometer laser. And the other thing is angular resolution. I don't know if it has a. Doesn't have that. It's quarter degree angular resolution. So the step size is pretty large between pulses. It's a 2 return system. In a room like this, in the middle, it will generate about close to 1 million points, which is not a lot for a laser system these days. So it's not nearly suitable for forensic, as someone said this morning, forensic analysis and so on. It's great for forest plot environments.
But what's the quality of the encoded measurements of the vision system? The encoder that you take and the measurements of the.
Oh yeah, no, the actual measurement, the rotation and so on is very good. It's
Even at large distances, you still have.
yeah, but because of that beam divergence, you get that smearing effect of foliage, especially. So what we've done is another student, Alex Fafard, actually developed an algorithm. Pretty, I don't say simple, I say elegant because it sounds better. But because you're scanning 270 degrees and rotating 180 to give you that 360 coverage, you're oversampling the polar region the whole time because you're crisscrossing there the whole time. So you're biasing your assessment. If you think about assessing LAI with this system, we realized very quickly you cannot really just use the raw point cloud and look at LAI because you're absolutely biasing your coverage right here in that hotspot. So he came up with a very elegant system to downsample and unbias the data set that you've got a representative distribution of sample points for something like LAI assessment. So now we always run his code first, but it's very accurate in terms of its angular measurements, step measurements, and so on. It's just a coarse system, Yeah.
So my second question is that you said maybe, hopefully I did not misunderstand. So is your objective to have it as close as possible to reality, or to have it, maybe can you say it's a simulation tool to generate training data for machine learning?
I think our goal is always to get it as close to reality, but with this big acknowledgement that we can never match reality. That's why I'm so fascinated by some of the tools that you're developing, right? For accurate, rapid assessment of environments where you can, in theory, use even photogrammetric approaches, not LiDAR even, and generate these kinds of input scenes for deer sit. So that answers that one component. Yes, we would like to get as accurate as possible. We want the corn specialist to look at our cornfield and say that you shouldn't cringe too much. They should say, "Oh, it looks like corn. It's not perfect, but it looks like corn." But the proof of the pudding is more important to me. And I'm trying to mention this. I know we're out of time, but I'll try and explain what I mean. I don't care if the corn plan is not perfect, as long as what it represents can be perfectly understood. If it represents a certain LAI, I want to be able to simulate it and extract that exact LAI. Is it exactly what a corn plant's LAI should be? Maybe not. But if my algorithm can untangle the trait, I hopefully can extend it to the real thing in a better way. So that is where the power of the simulation for me comes in. Is I have complete scene understanding. I can toggle switches of leaf angles, remove leaves, chop down trees at will, as long as the signal that I then simulate is accurate to what I did, even if what I did is not perfectly realistic. I think that's sort of I don't know if that makes sense, sort of recursive thinking.
All right. Well,
Thank you so much.
yeah, thank you.
That's the Nancy and all hospitality and everything. I really appreciate it.
Yeah, just an announcement, we have more presentation coming up, and yeah, join us if you can.
And so Lexi,